Hello and welcome to Algorithms Live. As I said on the blog, I made a long blog post about where I've been the last few months and what I've been doing and some of the changes I'm making. So this is the first episode where I'm running it in the new format. And this week I'll be covering this technique called fracturing search, which I think is one of the coolest techniques that I've come across in recent months. So let's begin on how this technique works and give you a problem that you can apply it to, and then just show you how you can apply this to a variety of other problems. Okay, so let's talk about spanning trees. So one of the things you can do is you could be given a graph like this just as a problem, and you could be asked to compute the minimum spanning tree. And so what the minimum spanning tree is, I'll just draw one out right here, is you select some subset of the edges. And so I could end up with a tree like this. And I want to be the sum of the edge weights, just 1 plus 2 plus 3 equals 6. I just want that to be the smallest possible out of all possible spanning trees of this graph. So every node has to be able to reach every other node, and it has to be a tree. So you can solve this a number of ways. There are a few algorithms. So I'll list a few out here. So we have Kruskal's, Prem's, Boruvka's. These are all just pretty well-known spanning tree algorithms, and there are many more that exist. And you can always find that smallest spanning tree. But what if you wanted to find the second smallest spanning tree or the third smallest spanning tree? So I'll draw a few more of these out. So we could do something like this. So we could have the smallest spanning tree is cost 6, the second is cost 7, the third is cost 8, the fourth is also cost 8, but we have a different tree that can get us that cost 8. And what we're interested in this problem is we want to find the kth smallest spanning tree. So helping out with the Yusuko campus here, what I ended up doing is I set a problem like this, and it had several different bounds. It was IOI style. It had a few different bounds, but the maximum bound was this. And so there are a lot of ways you could end up going about solving a problem like this. So if I look back at a previous episode, so if you go all the way back to episode 6, then I have this robotic cow herd problem that was a Richard Peng problem, and one of the ways you could go about solving this is you could do a binary search, and then with a little bit of cleverness in how you enumerated the solutions on that binary search, you could find the kth solution. There's also a few other techniques you could use that are involving cut spaces, and so those are fairly efficient. So there are a couple different ways you could solve a problem like this. But I can tell you that if you use the robotic cow herd technique, for this problem, it doesn't solve the largest batch, but some of the other techniques might also solve the largest batch. So what I'm interested in is going over this technique called fracturing search. And so I think this is a really cool technique. It's basically a generalization of a technique by Murty, so I can show this to you here. So he was looking at the assignment problem. So it's like a weighted bipartite matching. You can solve it with the Hungarian algorithm. And he was interested in finding the kth smallest bipartite matching in terms of having costs on those edges. And what we're going to be looking at is finding the kth smallest spanning tree. It turns out you can use the exact same principles and techniques to find a spanning tree. You can use this technique very generally to find the kth smallest solution for a whole range of problems. And that's why I'm going over the more general technique in this video. But we're going to start teaching the technique on spanning trees because I think it's a little bit easier to understand what's going on in the spanning tree case. Just realize you can apply it to a whole host of other problems. So let's talk about search spaces. So you could look at the spanning tree algorithm as a search problem. We're searching a very large search space, which is the set of all possible spanning trees. So there's quite a few of these. We can look at there's n to the n minus 2, and that's by this Cayley's formula. And as you can see, for our purposes, for the problem that we're going to solve, this number gets really big. 50 to the 48 is a very large number. This is a large search space to go solve. But it turns out we can solve this pretty efficiently and find the minimum spanning tree pretty efficiently using Kruskal's or Boruvka's or Prim's. And that gives us the MST that we care about for the search space. So if we want to find the second smallest algorithm, or the second smallest spanning tree, what we're going to actually do is we're going to fracture the search space into disjoint pieces that remove the MST. That's our goal. We want to just like take whatever search space we have, take it into a bunch of different pieces, and then on those remaining pieces, one of them, if I take the union of the minimum spanning tree for one piece, then another piece, then another piece, then I'll have the next smallest spanning tree, as long as I've somehow excluded the smallest spanning tree from the search space. So let's do that here. So as you can see, I've fractured my search space into a few different regions, and now I can find the next smallest spanning tree in each of these regions. And so one of these 5 spanning trees will happen to be the smallest spanning tree. So let's say the next smallest spanning tree is over here. And then in turn, what I can do is I can take that spanning tree, remove it from the search space, and then fracture the search space on that spanning tree. And I just like keep breaking it down this way. And I just keep a frontier of all the different search spaces I have left to search that haven't been explored yet. And then as soon as it becomes the kth smallest spanning tree that I've seen so far, I'll fracture off that search space as well. So it's a pretty elegant algorithm because it's just so generally applicable. But what we're going to do is you have to figure out, okay, things I haven't addressed yet are how do I characterize these subspaces that I need to search? And how do I break a search space into disjoint regions? I can't have overlap between these regions or else I might rediscover the same spanning tree multiple times. So that's what we're going to address next. Okay, so we can think about our graph as a list of edges that are basically all the edges in the graph. So if it's a complete graph, it's and choose 2 number of edges, and we're going to make a decision. So initially we're going to say you could take all these edges. So I'm going to give a label to each of these edges that'll tell me, oh, if I can take all the edges, I'll give it a label of 0, and that means it's free. So I can choose to include this edge or not include this edge in terms of my solution. I'm going to add 2 more labels here. This next label is 1. So 1 stands for definitely include this edge, and I'll add another label here, -1, saying definitely exclude this edge. Don't take this edge at all. So if I already give you some pieces here, so I'll say, okay, maybe this is still free to choose, this is still free to choose, but I definitely want edge 3, definitely want edge 4, don't take edge 5, don't take edge 6, definitely include 7 and 8. I can characterize certain pieces that these are already fixed choices all right here, but then 1 or 2 of these pieces could be free. What I'll be left with is I'll have some edges that I could potentially take or not. Those are the free edges. And then everything else is fixed, forming a forest on this tree. So it could look something like this. And so that's my forest. And I could find ways that I could potentially hook up the remaining connected components. And then I get my spanning tree. So I might have a choice, oh, maybe I have to pick this edge or not. But the subproblem that I'm left with, or the subspace of spanning trees I have left to search, could be characterized just by taking these 3 values for every single edge. Okay, so let's say I have a spanning tree like the one to the right here, and I have some of the edges I've already picked. Maybe this table goes on, there's some more edges in the graph, but these are the first 5. And what I want to do is I want to be able to say, okay, these edges were all open choices at this point, or maybe they were fixed, maybe they weren't. And what I'd like to do is I'd like to be able to fracture the search space so that it doesn't include this spanning tree, but then it's a bunch of other search spaces that we can run Kruskal's on and find out the next candidate solution. So here's the observation we're going to use in order to do this. If I exclude some edge from this spanning tree, then, and I say definitely don't take this edge, then it's going to produce a different spanning tree than the one I'm currently given. So that's what I'll do, is I'll just put -1s on the diagonal, and I'll just end up with 5 different search spaces, one for each edge in my spanning tree, and I'll have definitely excluded the spanning tree, meeting one of my goals. But this is a problem because if on a subsequent iteration, I try excluding edge 2 and then something else excludes edge 2, you can see these two search, or something else excludes edge 1, you can see these two subspaces are now the same. And basically what this means is we have overlap in our search spaces. We were trying to fracture it, but there's this common area between them that exists, and that's not very good in terms of us like fracturing the search space into different pieces. So we're going to do something a little bit different to guarantee that we definitely fracture this search space. If we are excluding edge 2 as one of our pieces, then we're saying we're definitely taking edge 1. And then if we're excluding edge 3 from this, then we're definitely taking edge 1 and edge 2. And then I still have freedom on my remaining edge choices. And so now what I'm left with is 5 disjoint search spaces that I have left to search for finding some other spanning tree. So one thing that I think is really cool about this technique so far is it's a search algorithm, but it doesn't have a scene table. It doesn't have some kind of visited array that we're keeping track of different states that we're seeing. Instead, what we're doing is we're just like characterizing where we have left to go. And I think that's just like a really surprising and interesting way of thinking about search. So let's take a quick look at an overview of like how this algorithm works and can kind of just see this in action. So when the algorithm kicks off, what we're going to do is we're going to have a priority queue. And this priority queue is basically sorted by its MST. So what we put in initially is a search space of all zeros. Everything can be taken or not taken for every single edge. And we compute the MST and throw it in this priority queue. So this priority queue is going to be sorted by the minimum spanning trees. So we'll take this item out of the priority queue, and we end up having a search space over here. So now we fracture this search space into pieces. And then for each of these pieces, we compute some kind of spanning tree. So in this case, we have 4 different pieces. And then we throw them in the priority queue to be sorted. And so those are the 4 different pieces I have left to sort. I save this as the first spanning tree, whatever. And now these pieces are sorted. And so I just take the next piece out of the priority queue, just remove it here. And then for this piece, we're just going to fracture it again. So I find this, I already have this spanning tree. And so then I just fracture it into 4 different pieces, put those 4 different pieces in the priority queue, rinse, repeat. And then if I run this k times, the kth thing that I pull out of the priority queue is the kth smallest spanning tree. So I think this is pretty elegant. What I want to do next is just actually code this thing and just show you how to implement it in Java. Okay, so let's talk about the code that I have so far. So this problem was called Happy Trails in the Usico camp. And so what I've basically just coded so far is I've just read in the graph is a list of edges. I've sorted those edges because I'm going to be running an MST algorithm. I don't need to sort the edge every time. I can just call this sort once. I created a disjoint set. So what you have here is just an edge class. It does comparisons on the weights, and then the disjoint set is just your standard disjoint set with union by length and path compression. I haven't done an episode on this yet, but that's you can just look up disjoint set code. And I'll be using Kruskal's algorithm to find my minimum spanning trees on my subspaces. I'll be showing you how to do that. And then everything else is just going to be this fracturing search algorithm. Okay, so the first thing we need to do is we need to put in something to hold each of our partitions once we form a partition. So let's just write the code for that here. And I need to be able to sort it because I'm going to be throwing this in a priority queue. So So I'm going to have two arrays. The first array is characterizing the subspace. It's basically saying like what choices did I make to get to this partition. So this is really just a subspace of my search space. I'm going to also save what the MST cost is. So I'll store that once I find out what the MST is. And then the last piece I'm going to have is the actual edge IDs of the edges I've taken. So what index in this list of edges, and that's going to just hold what my MST actually was based on the choices I had. Okay, so let's put in the constructor. And so that's my constructor, and then the next piece down here, I want to add a comparator. And so that's just going to be my MST, just comparing which search space is currently the best one and the one that I want to fracture next. Okay, for the next piece, let's just start thinking about like two functions that we need, and then I can write one in terms of the other. So this first one is it's going to create a new partition, so I'll call it createPartition. And it's just going to take in the set of choices that I've made so far. So this is that 1, 0, and then -1, depending on if you are guaranteeing to exclude something or include something, or if we still have a free choice. For now, I'll just return null, and I'll fill that in later. And then I'll just like write the driver of the algorithm, assuming I have this createPartition function. So createPartition will create a new partition using these choices and also compute the MST. That's how I'm thinking about it right now. So then I could write a solve function and then just pass in this value k for what I want to print out. So I'll just do a print something like this. So it just takes in the input, prints that kth MST. And for now, I'll just return -1 if it fails to find something. So like I said, we're just going to have a priority queue. And then the next piece is just create the partition. And Java will just fill these in with all zeros. So this is just going to create the minimum spanning tree that exists and adds it to the queue to kick off the search. So this will look a little bit like Dijkstra's with a priority queue or any of those algorithms. So if I still have stuff to do, I just take out the next partition, which is a lot like taking out like the next thing to search. So just decrement k, and if k equals 0, then I've found my answer, so I can just return the cost of the answer. Okay, so now I have to hit that next piece of the code. So I actually have to consider constructing a partition. And so what I'm going to do here is I'm just going to loop through all the edges in my desired MST. So if I look down here at partition, I actually have the MST edges. So I'm just going to do exactly what I was saying. I can exclude taking the first edge, then take the second edge, exclude taking the second edge, and then take the third edge. So I will go do that here. So one thing I'm going to do is if it was a forced choice, yes or no, and I guess it could only be yes, then that's when I make the new fracturing because I'm actually putting a 1 here or a -1 here. So I'm just making a small change in the code. So I just like copy all the choices I made for the subspace. Exclude the current edge that I'm considering. And if you remember, I have to make every edge up to that choice. I'm definitely taking it. So I'll do that here. And we know if this edge is in our MST, it's either a 1 or 0. So I'm just going to fill these with 1s. Okay, so let's consider constructing the next partition and just throw it in. And I'm actually going to design this next piece of code a certain way. If it could be possible that I exclude some edge and I could end up with something that, like a search space where it's not possible to form an MST. So let's say there was only one spanning tree. If I exclude any of the edges, or if one of the edges is a bridge, then I'm just not going to have a possible spanning tree. So in that case, I'll return null from createPartition. And in that case, I just don't want to add it to my priority queue. So if it's not null, so this will, in practice, affect our runtime a little bit. It'll make it a little bit faster than our runtime analysis will yield. But that's okay. But this is something to keep in mind when you use this algorithm. Even though it's got a certain big O, that big O may look ridiculous. This prunes a little bit, which is nice. Okay, so let's come up here and deal. So this is the whole solve algorithm. But the next thing we want to deal with is just this createPartition function. If we can successfully compute the MST, create a new partition object, then it can go in our queue to be fractured in the future. So let's just do that up here. Okay, so one thing I'll choose not to do is use the disjoint set, create a new disjoint set. So I add a reset function to my disjoint set, just creates, so I'm just reusing the memory as I go. And so now it's basically crustals, but I need to do a little bit of extra work. So these are the edges that I'm going to take in. So they're n-1 edges in any tree if my graph is size n. And I'm just going to fill this with -1 so it's easier to debug if I end up having a bug. It'll get an array out of bounds error and I'll know where my bug is. Okay. So the first thing I need to do is I need to go through all the edges that are definitely in my answer. So there'll be 1 in choices, and I need to union those two disjoint sets with, or two different sets in my disjoint set, and before I even kick off crustals. So that's what I'm going to do first. And so pointer is just storing like where I am in terms of my MST construction. So it's kind of constructing the MST out of order, but that's okay. I'll just like sort it after I'm done or something. Make it a little easier to code, or I could keep it out of order and I think it would still be fine. So the next piece is, this is actually just running crustals, so I'm just looping through my edge list for all the edges that are still an open choice. So I'll only consider taking it if it's an open choice, because if it's excluded, pretend it's not in the edge list, And if it's already included, well, this for loop already covered it. So that's what that's going to do. If I ever get to the point where I've unioned everything, then I have a tree, so I can just break out of this loop. Otherwise, I just look for my free choices, something like this. So then I look at the edge, and if it doesn't union two families, if they're already connected, adding this edge would create a cycle. So I just have to make sure it's joining two separate families. And if the edge is going to join two separate families, then I just union those two pieces together. So just standard cross goals up to this point. I'll just put in a check here. So if I ever get to the case where I've failed to join, I've gone through all the edges I could possibly add, and I failed to join it into a tree, then this search space doesn't have a minimum spanning tree, so I can just throw it out. So I just return null. And then this piece is also helpful. I'm just going to sort the MST edges and return my new partition. And that's all I have to do here. So I think that's everything. I think I don't really have anything else I can add or need to add to this problem. So let's see if I can compile. Oh yes, I use choice instead of choices. All right. So let's go snag the sample input. I think that's right, so let's just take a quick look at the data. Yeah, so it at least passes samples. So let's just go submit it. You can see it's doing quite well. One thing I'll say is the computer that I'm running this on is just a Surface. So it's running a lot slower than it would on a faster computer. So I have a laptop that I do competitive programming on. I don't do that on my Surface typically. And so these times would normally be a lot faster. I think the worst case on this problem on my laptop is under half a second. But it's a little bit worse just locally. I think the time limit on Propagate, which is the contest management system we use at USICO, I think the time limit was 2 seconds or something like that. So yeah, it's like 3 second run. But this was the actual data. Oh wow, so 5 second one. But as you can see, it just passes all the data and we're doing pretty well. So the next thing I want to do is just talk about how you go about analyzing this problem and what do you need to know in order to do fracturing search successfully. All right, so let's talk runtime and memory consumption in terms of the code that we just wrote. So that createPartition function, let's think about how fast that runs. So it basically just runs Kruskal's algorithm, and our edges are already in sorted order, so that makes things a little bit easier. Kruskal's runs an m times inverse Ackermann of n, so the function like that. And so that's just going to be the dominating factor of runtime of createPartition. So then the real bottleneck, the priority queue piece, like could be a sorted array where we just like take out the minimum element as we go, or just using a priority queue for convenience. So it's not really the dominating factor. So the dominating factor is how often does createPartition get called, and that ends up being, well, think about it. If you have some kind of spanning tree, so I consider excluding every single edge at least once, and I make a partition considering excluding each of those edges. Well, in an MST, there are n possible edges. And then how many times is that going to get called? Well, that loop to go through every single edges gets called k times, where k is the kth smallest MST. So our runtime ends up being this. So O of k times n times m, inverse sacrament of n. So that's actually pretty fast when you think about it in terms of this problem. This basically is not going to be more than like 3 or 4. In practice, it's actually pretty fast. So I just think of it as a constant, and the algorithm is a little bit closer to this when I do my runtime analysis. And this lies a little bit because if you ended up, if you remember, there were certain partitions where you'd run through the whole partition, it would kill a search space. So you'd never have to consider that search space again. So that's like saving a little bit of runtime. It's a very tight loop, like the deepest loop is pretty tight. So it runs pretty fast. And then the memory consumption is, at worst case, we have to store all our choices, which is O of m in size. So you get something like this for memory usage. So we have up to k things we're going to be throwing in our priority queue, and or O of k things thrown into our priority queue, and then we end up using m memory for each of them. All right, so let's just talk about, like, this is a pretty generally applicable algorithm, but when can I apply it? Like, what things have to be true in the problem I'm caring about in order to make this true? So let's look at a few properties that will tip you off that you could go down this route. So the first piece is it needs to be some kind of decision problem. And so what I mean by this is you basically just have a list of decisions you need to make, yes or no. So you can think of like knapsack meets this property. In this case, like spanning trees meet this property because you're either taking an edge or you're not taking an edge. Independent set meets this property. Clicks meet this property. You're picking a subset of edges. So if you're picking a subset or a subsequence, this is a good algorithm to consider. So the second property is you need to be easily able to find the minimum or the max in your subspace. So the minimum spanning tree you can find fairly efficiently. There are other algorithms where you could easily find, given some forced decisions, what the answer is. Independent set is too hard to find the answer to this for the min and max of the subspace. But if you look at the assignment problem, you just run Hungarian algorithm, for example, and your decisions are, am I taking this edge in the matching or not taking this edge in the matching? Then it's really easy to find the minimum and maximum once you fix some of those decisions. And so then the last piece that needs to be true. So the last piece is maximum solution must have maximal choices. What I mean by this is the number of ones that you take in the subspace. You can't add more ones to it and get some solution in the maximum solution. So it needs to have a maximal number of ones to be considered a search to characterize. So a good example of this would be knapsack. When you have your optimal knapsack solution, you shouldn't be able to add items to the knapsack. You'll also notice that if knapsack items could have negative weights or negative costs, then that actually might be true. It might be better not to include something into the knapsack, but that you potentially could include in a solution. So if it had a negative reward, that would be the case. So you wouldn't be able to use this algorithm in that case. But this isn't a lot of criteria that you really need to solve this problem. There's a lot of, I think, problems that fit this criteria. So I feel that fracturing search is very applicable to a wide range of problems. Another thing is I think this algorithm kind of combines well with other techniques. And I plan to do a few more episodes in the future where I can show you those combinations. I've been thinking about weird ways you can use fracturing search to solve problems that's really not intended to be solved. So I'm going to be looking for some example problems over the coming weeks and make a few more episodes on this because I just really like this technique and I think it's applicable in a lot of places that you wouldn't find it applicable. So I hope you all enjoyed this episode and I'll see you guys next week.